In this video, we're going to prove that LP spaces are complete for any choice of P greater than or equal to 1. So this is a stronger version of something that I proved in another video, which is that L1 is complete. But this requires a more general argument. So we have LP. This is the space of sequences such that their LP norm, which is the sum, is a finite number. So we're going to suppose that we have the following. We have XRN, and this is going to be a Cauchy sequence in LP. So the R in this case represents which sequence we're looking at, and the N represents the individual numbers in the sequence. So X1N refers to the sequence X11, X12, X13, ... So this is a sequence of numbers in LP, real numbers in LP. For R equals 2, we have X21, X22, X23, ... and then so on. So you can think of these sequences as lying in kind of an array, and you can think about the columns of this array. So you can think about, basically for a fixed n in n, just the numbers in the nth column. So just the first column, just the second column, just the third column. And what do we know about each of those individual columns? Well, we know that this is a Cauchy sequence. So we know that for all epsilon bigger than 0, or let's let epsilon be bigger than 0. So we know that there is a natural number n such that for all, if I and j are natural numbers at least as big as n, then the following holds. So the sum over all n of, sorry, not xr, xin minus xjn, or actually, let's write k. Xik minus xjk to the p power to the 1 over p is less than epsilon. Or if you like, you can raise both sides to the p power, and you get xik, xjk to the p, summed over all k, is less than epsilon to the p. Great, but if you think about it, this is true for if the I and j are sufficiently large, and then it's true if you sum over all possible values of k. So it's kind of like taking all of the different possible columns of the array, essentially. So what that means is that if we fix a specific number n, so fix a specific column, then again, if I and j are large enough, xin minus xjn, just that value to the pth power, well, this is definitely less than or equal to this whole sum, and so this is less than epsilon to the p. And in particular, that means that for I and j large enough, xin minus xjn is smaller than epsilon. So what this shows is that for each fixed n, the numbers in the nth column of the array that I was writing before form a Cauchy sequence. So it follows that as r goes to infinity, so we have xrn, this converges to something, right? Which I'll just call Sn. And we know more. Notice that if we take a finite sum, so if I sum over n equals 1 to some fixed number n naught, and I'm going to sum, let's say, xin minus xjn to the pth power. And I know that this expression is less than epsilon to the p if I choose the I and j to be large enough. But I can take the limit of this as j goes to infinity. So I can fix the I and let the j go to infinity. And because this is just a finite sum of numbers and I have continuity of the absolute value, raising everything to the pth power, etc., so that tells me that the sum from n equals 1 to n naught of xni minus Sn to the p is less than epsilon to the p, or that this expression to the 1 over p is less than epsilon. And again, I'm using the fact that if I let the number on top go to infinity, it converges to Sn, which is what we just proved before. But now notice that I can take the limit of this expression as n naught goes to infinity. And again, sort of by continuity of everything in this expression, I get that sum from n equals 1 to infinity of this expression here to the 1 over p, that this is less than epsilon. And again, I'm assuming that I is just sufficiently large here. And so what this shows is that this sequence Sn that we produced is actually the limit of xrn with respect to the LP norm. And so this is half of what we want to prove that this space is complete, because we produced a sequence that is the limit of xrn. And so the only thing that is left to show is that the sequence Sn is itself an LP. So how we're going to do that is I'm going to again assume for right now that I have some kind of finite sum. So I'm just summing from n equals 1 to n0, if you like. And I'm going to sum Sn to the p to the 1 over p. And where we want to eventually get with this is that if the n naught goes to infinity, that this is bounded. But to start with, we can use the Minkowski inequality for finite sums. I can write this as xni minus Sn to the p. And then I'm allowed to do this for any I that I want. Sorry, that's not right. This is, what is this? This is xni minus xni plus Sn to the p. There we go. But the reason I want to do that is because now I get that this is less than or equal to n equals 1 to n naught. And I'm going to have Sn minus xin to the p to the 1 over p. Again, this is just for any I that I care to choose. And then plus some, I guess I'll put this over here, sum from n equals 1 to n0, absolute xin to the p to the 1 over p. And again, this is by Minkowski bound for finite sums, which is kind of like Minkowski inequality for integrals. Okay, great, but this expression here, I know that this is bounded. And the reason that I know that that's bounded is because xrn is Cauchy. And being Cauchy in a metric space implies that the sequence is bounded. So there exists, I don't know, call it R, so that for any choice of R, I have this. I have that the LP norm is less than or equal to R. And so that tells me that with this expression up here, this is less than or equal to R plus this sum right here. But I also know that, xin converges to Sn in the LP norm. And so I know that if I choose the I to be large enough, then this is less than epsilon. Okay, great. But now notice that I have that this expression right here is less than or equal to r plus epsilon. And this argument really didn't rely on my choice of n naught. The n naught can just be anything that I choose for it to be. And so if I take the limit as n naught goes to infinity, I get what I want, which is that the LP norm of Sn is bounded by r plus epsilon. So there you go. We produced a sequence which was the limit with respect to the LP norm of the sequence right here. And it's also an element of LP. So that is the end of the proof. Thanks very much for watching.